Some cyber attacks don't rely on tricking users at all. They exploit mistakes in how applications are written. In this video, we'll break down application vulnerabilities, focusing on how attackers take advantage of system memory and poor coding practices. One common application vulnerability is memory injection. Memory injection occurs when an attacker inserts or manipulates code inside the memory space of a running process. This allows the attacker to execute their own code or change how an application behaves, often while appearing to be a legitimate process, which makes detection harder. Another major vulnerability is the buffer overflow. A buffer overflow happens when an application tries to store more data in a memory buffer than it can handle. When extra data is added, it spills into nearby memory locations, overwriting information that was never meant to change. This can cause programs to crash or behave unpredictably. The real danger of buffer overflow attacks is that overwritten memory may include critical information like return addresses. If attackers carefully craft the overflow data, they can force the program to execute unintended instructions, potentially giving them control over the system. Closely related to buffer overflows are integer overflow attacks. These occur when a program attempts to store a number larger than the maximum value an integer variable can hold. Instead of stopping safely, the value may wrap around or reset, causing unexpected behavior that attackers can exploit. Another category of application vulnerability involves race conditions. A race condition occurs when multiple processes try to access or modify shared memory at the same time, and the outcome depends on which process finishes first. Poorly written code allows these processes to race, leading to inconsistent or unsafe results. A specific type of race condition is the time of check to time of use issue. This happens when a system checks a condition, assumes it stays the same, and then acts on it later. If the condition changes between the check and the action, the application may crash or behave incorrectly. Finally, malicious updates are another serious application vulnerability. A malicious update looks like a legitimate software update but contains harmful code. Attackers may distribute these through fake update prompts or compromised update servers, leading to malware installation, data theft, or system compromise. Defending against application vulnerabilities starts with secure coding practices, regular testing, and applying updates only from trusted sources. Developers must validate input, manage memory safely, and protect shared resources to reduce these risks. The key takeaway is this: application vulnerabilities exist because software is written by humans. When attackers understand memory, timing, and update processes, they can turn small coding mistakes into major security breaches.